we go. Hello, everybody. Thanks for finding your way here. Maybe we'll go with that. Okay. All right. Today's lab, let's see, Rep 9. I'll just, oh, good to see. Let me see who all is here. Sam, Reagan, Rockford, Elizabeth, Shelby, Jack, Jonah, Darren, and me, of course. Today's lab activity is mainly visual. It's mainly about drawing vectors on a kind of a fairly blank sheet. Turning off my phone ringer. I'll be basically, in our time together, I'm going to talk through the different files that are up on Moodle. There's 4 of them. One is the lab manual, although I think that one's called lab number 10. Although there's nothing in there you really need to turn in. There's just information and steps for you to follow. There's a couple spots on there where you're asked to record information, but you don't need to do that because you can just record the same information on the other 2 pieces that I'm going to have you submit to me. And the 2 pieces to submit are called the worksheets and data sheets. There's kind of two different collisions that you're going to address. And for each collision, you're going to draw a variety of vectors. And on the worksheet, you're going to draw vectors on the worksheet. And then you're just going to make some measurements off the worksheet and record those key pieces of data on the data sheet, which is an Excel file where you can just kind of input some key numbers into some key cells. And I think that's all that would need to be done on the data sheets on Excel is kind of enter values wherever there's a kind of an underlined blank prompting you to put a number in. You could probably erase the underlines and put the numbers in. We'll see that in a little bit. Let's see, up to 12 people. That's good. Hello, Lauren. Hello, let me see, Jacob, maybe. I've gotten labs from last week from several of you, or a good number of you. They're looking pretty good. Yeah. I'm just going to say one thing and maybe just wait a couple minutes, see if some other people arrive before I start going through the key information for this week's activity. In some of the lab submissions from last week that I've looked at, I think the calculations looked, the information in the data tables, the calculations and the conceptual questions or the analysis questions looked very solid overall. If there was one part that kind of grabbed my attention, it was in doing let's see, there's 3 parts to last week's lab: the race, the loop, and ballistic pendulum. If there was one part that caught my eye, it was on ballistic pendulum. No, sorry, that's not right. It was on the loop and not on recording the experimental data, which I think we mainly did together. It was on doing the theoretical calculations. I just want to emphasize one thing, if maybe you're still thinking about that or looking at that. The only number provided to you that is needed for that calculation, for the calculations about the theoretical analysis of making it through the top of the vertical loop, the one and only number you need to get started is the radius of the loop, which I believe was around 11 centimeters. So no other numbers from the experimental data piece of paper, which is the previous page of the lab, are needed there. Okay. Good, we're up to 13. That's great. Okay, I'm going to pray and we're going to get started. And I think I mentioned in a couple places that I think probably only about 45 minutes together here, for maybe less, for me to kind of explain what the lab um, apparatus looked like and what the data sheets represent, what each mark on the data sheets represents, and then to go through what I would like you to draw out. And again, today is a very visual lab. We're using things like protractors and rulers, straight edges. We're drawing vectors on a piece of paper that's kind of just a broad white, blank white sheet with a couple key marks given to you. I was going to say something else. Can't remember. Okay, so I'm going to pray and we'll get started here on April 2nd, our second lab of Quad 4. Dear Lord, we just ask that in this time together we could have our other thoughts, which are swirling around. I know that's the case for me, just kind of fade into the background, and you allow us to focus and work together on some physics today, although we are spread out all over the place. I also just bless the conversations, emails, and decisions that are being made for everyone about registration for the coming semester, which I'm looking forward to quite a bit. That's a lot. That's a big point in any school year, is making those decisions. And I just ask for your hand over all that and us today. Thank you, Lord. Amen. All right, collisions in 2 dimensions. So let me think back. Before break, we had a lab which was the 1D collision between the blue cart and the blue cart, red cart on the one-dimensional tracks. And we had photo gates that allowed us to measure velocities, scales to measure masses, and photo gates to measure velocities. Oh, I just remembered there's one piece of paper I want. Okay, I can reach it. And then last week we did a lab about energy, investigating mechanical energy, potential energy, kinetic energy, and trying to investigate conservation of energy in a couple different scenarios, things moving up and down. Today's lab is collisions in 2 dimensions. So what is the core concept when analyzing collisions? Momentum and conservation of momentum. So the core concept today is there's going to be 2 objects, as there were before. So like an object number 1 and an object number 2, and then initial and final, or you could say before and after. So our core idea here is we're going to check for conservation of momentum. And that would be P1 initial plus P2 initial equals P1 final plus P2 final. But these are definitely today going to be the vectors conservation of momentum in 2D. Now, what's one way to deal with vectors? A really good way to deal with vectors is choose an x-axis and a y-axis and split all the information into components, maybe using I hat and j hat to kind of write things out neatly. We are not going to do that today. We are just going to directly draw the vector arrow for P1 initial on the sheet, P2 initial, add them and have another vector on the sheet which represents total initial momentum. And then same thing here. So we're going to have several vectors on the sheet. Of course, how do you calculate momentum? Mass, which is a scalar, times velocity, which is a vector. So the core information you're going to see on the data sheets, worksheets, which I'm going to show you soon, are some dots which represent velocity vectors. Let me try to describe the arrangement. It's going to be a little hard to describe. So what was actually done physically in the lab, what would be actually done physically in the lab is at table height, there was a little ramp and a marble would be placed at the end of the ramp. I'll try to draw it here. So The side view would look a bit like this. There'd be the floor, and there'd be a table. And then on the table would be like a curving ramp. And it wasn't very long. It was just a it was just about a foot long. It was just about a foot long. And there was a little target object sitting right here on a thin little post. So there was a target object, I'll draw it in blue, and it was a marble. They weren't nearly this big, but it was a marble, and it was stationary. And then another marble would start at the top of the ramp, and it would be released from right there, and it would descend the ramp and collide, hitting this marble right at the edge of the table. And this marble was just resting on a fairly narrow little support post, just sitting there ready to go, ready to fly. And when it gets collided, this would, so this would descend, hit this marble, and then they would both go flying off, and they'd fly outward, and they'd land on the floor. And the landing points on the floor could be recorded by by putting down a piece of paper with some carbon paper, which we used maybe back in January. And where blue marble impacts the floor would leave a little dot on the carbon paper, and where red marble would impact the floor would be another dot. So if you imagine looking at this from top down, you would see these guys. It was not a head-on collision. It was not a perfectly straight 1D collision. These guys were offset a little bit this way. So when they collided, they not only headed leftward, they also kind of spread out. Maybe the blue marble kicked towards us a bit, and the red marble kicked away from us a bit. So this is the side view. And these guys would kind of fly outward. Maybe this guy would fly outward and hit here on the floor, and the red guy would kind of fly outward and hit somewhere else on the floor. And we could record the impact locations. So the height of the table is the vertical motion of the marbles is not the focus of today's lab. Imagine you're doing a top-down view, and you're just seeing this from like the ceiling downward. What we're really interested in is not the vertical motion, it's the horizontal plane. How far, what direction did the blue marble kick towards us? How far did it travel? Red marble kick away from us, and how far did it travel? So this is the side view, and the more common view that almost all of the visuals provided are a top-down view. So here we go. Let's see here. I want some Adobe files. Okay. So this one is called Lab 10 PDF. I don't know why I called these Lab 10. It's really our 8th lab. Not a very big deal, but this is all called Lab 10 sheets. So what does it say we're going to study? Study collisions and the conservation of momentum in 2D. Practice doing vector calculations graphically. Now, Monday's test is about momentum and energy. So it mentions energy a little bit, but clearly the focus here is on momentum if we're talking about collisions, and the focus is on vectors. Practice doing vector calculations graphically. We're going to do scalar multiplication graphically, visually on the sheet, and we're going to do vector addition because in order to analyze a collision, we need to find the total initial momentum 1 plus momentum 2 before the collision, and we have to do vector addition afterwards as well. So this would maybe be a top-down view of the collision here. And if you look at this, you can see like this lightly shaded guy would be what on the picture here is blue. Object 1 is the marble that starts at the top of the ramp and descends. It's kind of the incoming object. And number 2 is kind of the target object. Number 2 begins at rest. It is just sitting there waiting for something to descend the ramp and collide with it. And you can kind of see a little bit in this sketch here. It's not a head-on collision. So we get some lateral motion for both the darker M1 and the lighter M2. There's 4 four velocities to keep track of. Velocity of one before the collision, velocity of two before the collision is 0, so that's kind of one that is not very impactful. And then velocity 1 after the collision and velocity 2 after the collision. Now on the file I'm going through here, I think they call this one is called V0, and this is just 0, so it doesn't really get much of a name. V0, and this is V1 and V2. You could very easily, I could imagine calling this V1 final and V2 final, because I think that's really what they stand for. We would like to calculate capital PI, initial total momentum, and capital PF, final total momentum. So before is very easy because there aren't two contributions. One object starts at rest. So the initial total momentum is simply the momentum that the red guy has when he reaches the bottom of the ramp. Right here, he's moving at a high speed directly at the blue guy, or directly horizontal, I should say. So that one's pretty easy. That's mass 1 times V naught. The final state has two moving objects, M1 V1, M2 V2. From this, we see that the core data needed for this lab is you need to know the mass of object 1 and the mass of object 2, and 4 marks on our worksheets. And what are the 4 marks? I need to know, okay, the masses are mentioned. I need to know where the blue guy landed, where the red guy landed. They land at the same time. So by knowing where they landed, we've kind of, we've recorded their locations at the same moment in time. So I need to know where the 2 outgoing guys landed. That's 2 of the key marks on the paper. That represents the final state. But what else do I need to know? I need to know something about how fast the red object was going before the collision. If there had been no collision, I need to record something about how fast the red guy is going at the bottom of the ramp as he's about to collide with blue. And so to do that, we also just did a collision where we also just ran it in lab. We would run the red guy down the ramp with nothing to collide with, and we would just watch him sail outward and land. So there's 3 landing points. There's where the red guy lands in the absence of a collision, which represents before interacting with anything. And then there's where red lands after and where blue lands after, so 3 landing points. But this mentions we need a 4th mark on the sheet. What's the 4th mark on the sheet? The 4th mark on the sheet is I need to know this location right here. I need to know this location on the ground. Where on the ground is directly below the collision? I basically need like an origin. I not only need to know where things end up, I need to know where they all emanated outward from. And the point they all emanated outward from is going to be called the collision site. So a 4th mark indicating the location where the collision occurred, parentheses, the common origin or tail of all 3 velocity vectors. I'm going to come back and say something about masses here. I'll give you some numbers for mass. There's just basically 1 or 2 decimals to fill in to some of these blanks, or just to record on your own. Again, you don't have to hand in the Lab 10 PDF that I'm going through. What you need to hand in is the worksheet and data sheet. Okay. So we are going to have, okay, so this is what a data sheet might look like, and I'm about to show you a couple of them, really. Whoops. Let's go. Okay, so this is what a data sheet might look like. 4 marks. Steel on plastic. So I'll talk about that. There's 2 types of collisions. You could have a steel marble collide with a steel target, or you could have a steel marble collide with a plastic target. And I'm going to give you, you're going to analyze 1 collision of each type. So for example, this might be what an 8.5 by 11 sheet of paper looks like for a steel on plastic collision. So object 1, steel, object 2, plastic. I'll talk about the masses in a bit. I just want to go through the visuals. So this is where the collision occurred. This is like the origin. If there had been no collision, the steel sphere would have gone and landed right here. But with the collision, we have the steel sphere kick to the left or to the top of the sheet and land there, and the plastic sphere kick to the right and land over here. And I don't think these dots are really representative of an actual collision, but just to show you, there's kind of like a central axis from origin to straight ahead in the absence of a collision. And then with the collision, one thing kicks to one side of that central axis, let's say upward or leftward, and the other object kicks downward or rightward. Okay, what will that actually look like? And there's the, oh, sorry, I didn't need to do that. What will that actually look like? Lab 10 demos is for you to kind of see what somebody has done in a past semester for drawing all these vectors. Lab 10 worksheets, I'd like you, ideally, the expectation is that you could print out the Lab 10 worksheets, and there's 2 pages here, and then you could, with a ruler, with a protractor, with a straight edge, you could draw all the velocity vectors that are needed and all the momentum vectors that are needed. And to give you an idea what that might look like at the end, we'll look at a demo sheet. But first of all, what do we got here? So this was a steel-steel collision. So I'm going to call one of them steel number 1 and the other one steel number 2. Steel objects have a high mass and they're the same. Plastic objects have a lower mass. So where's the collision? Collision in black. If there had been no collision, steel 1 would have landed right there. With the collision, steel 1 actually landed over here and steel 2 actually landed over there. So that's your 4 key data points. And you're going to basically draw several vectors that emanate from the collision site outward to other key points on the sheet. What would the next one look like? Okay, steel on plastic. Collision site, steel before the collision, without a collision would have landed there. Steel after the collision. So a slight difference is, in this case, the moving steel guy kicked to the left and the target kicked to the right. I think up above here, the steel guy, anyways, blue kicked downward and green kicked upward. Not that that's a big difference, but you kind of see that. So these are your data sheets. The only number, like I said, to fill in is some mass information up here. And then there are several vectors to draw. So I think what I'm going to do now is I'm going to discuss the mass information and give you 1 or 2 key numbers. These are the only key numbers you need that aren't just in the provided files. Just a second. Okay. So what is a topic that, of course, I love to talk about, and most, I think, science and engineers and physicists like to talk about? I'd like to talk for a little bit about units of measurement. Today's lab has fairly unusual treatment of units. We are not going to have very many units in today's lab. When you're asked to fill in momentum values, velocity values, or kinetic energy values, in today's lab, you do not need to put units on those. They're all going to be measured in kind of like arbitrary non-standard units. So with that in mind, I'd like to talk about mass. There's only 2 masses to keep track of in the problem. Mass of a steel marble. The steel and plastic are the same size, but the steel, of course, is more dense. And so the steel mass is higher than the plastic mass. So I'm going to tell you these 2 numbers right here. Record the masses of the steel and plastic spheres in grams. So you're going to want to write these down. They're quite small. They're physically, the marbles are pretty small. So the mass of a steel marble, I'll probably write this up on the board here, is 8.39 grams. Mass of a steel is 8.39 grams. The marble that descends the ramp is always steel. In the first collision, the target marble is also steel, but in the second collision, the target marble is plastic. Sorry, these are capital. I maybe should follow the notation in the lab. This is capital MP and capital MS. and mass of plastic is 2.67 grams. So these are the masses measured in grams. But as I said, in today's lab, we're not going to be too tied to any particular unit system. And we're going to make a choice which is going to make your life a lot easier. So these are, of course, in grams. But we are going to switch over to just kind of arbitrary units. What did I call them? Rescaled masses, if you read here. Now divide each mass by the mass of a steel sphere. This will rescale the masses from grams to more convenient units in which the steel sphere is kind of dictated to have mass 1. We will use these rescaled units throughout the lab. So I guess I called them rescaled units. Okay, and I guess I did that as lowercase m. Lowercase m was rescaled values. Uppercase m is grams. Okay, how do you get from here to here? Divide by mass of steel. So if you look on the sheet, if you can see on the screen, what is lowercase ms? It's 8.39 divided by 8.39. So we're just going to kind of shift to units where anything that's made of steel has mass 1. Now, that's kind of convenient because what do we have to do to calculate momentum? Momentum is mass times velocity. But if we're doing that calculation for a steel object, we're just doing velocity times 1, which of course doesn't change the number. So anytime we see a vector on the sheet, which is, let's say this is, I'm going to call this V1. V1 was the velocity of a steel object. Now I'm supposed to put another vector on the sheet to represent momentum number 1. Well, how do I calculate momentum? P1 is M1 V1. So I should take this vector and I should multiply it by the mass of a steel object. And the mass of a steel object we just forced to be 1, which basically means this arrow could either be called V1 or the exact same arrow could be called P1. Because the only difference between velocity and momentum is mass, and we've just kind of rescaled to give this object mass 1. So it's a time saver for us to do this. What is mass of a plastic guy? So what is the ratio of 2.67 over 8.39? 2.67 over 8.39, I came up with 0.318. And I think 0.318. And again, I'm not going to write units on these guys. I'm just going to, if you wanted to, you could just kind of make up a name for the units, or you could just call it like U for units. It would be definitely incorrect to write something like grams or kilograms because we don't mean 1 gram, we don't mean 1 kilogram. Okay, so backing up to here, what if instead of this object being a steel object, what if this was the velocity vector, I'll call it number 2, what if this was the velocity vector of a plastic object? Okay, P2, M2, V2. So what should I do with this vector? I would like to, on the whiteboard, draw another vector that represents the momentum of this object. So what I would do is I would get out a ruler. I've got a little ruler built into here. I would get out a ruler. I'll go back to just the full screen view. I would get out a ruler. This one isn't quite long enough. And I would measure the length of this. And let's just say, for the sake of argument, I measured the length of this, and I got a length of it would be, let me get close to what I've got on the screen, not that it really matters. 24 centimeters. Let's say I measured and I got 24 centimeters. Now, centimeters are not truly units of momentum or velocity, right? But I'm just going to measure the length of it on the piece of paper or on the whiteboard. And then what should I do with 24? If that represents V2, I should multiply by mass of the object. What's the mass of this object? The mass of this object is 0.318. So I'm going to take 24 centimeters and I'm going to scale it back to 31% or 32% of 24. So here we go. What is 24 on my calculator? What is 24 times 0.318? And my calculator says 7.63. So then I would get out my ruler and I would draw a vector parallel to this vector. Momentum and velocity are parallel, but they're not the same length because one has been scaled by mass. And I would lay out on there 7.63. And that would be about, that long. And I would label this shortened vector, I would label that shortened vector P2. Let me try to get in there a little closer. So I would call that shortened vector P2. And I might have made it a little too short, but this kind of sheds some light on why do we call mass a scalar? Because what did multiplying by mass do to the green arrow? It didn't change the direction of the green velocity vector, but it scaled it. It just scaled it back. It could have scaled it longer if the number I'd multiplied had been greater than 1, but it's less than 1, so I've scaled it back to something short. And anytime you have a plastic object in your analysis, which doesn't happen too often, but it does happen, anytime you have a plastic object in your analysis, you have to scale the velocity by 0.318 to come up with a momentum vector. Okay. And so at this point, I think I'm just going to pause before showing you the demo sheets. The demo sheets are an example of of all the vectors that need to be sketched out on your worksheets. Before doing that, just questions about what I've said so far and the masses and what the 4 dots on the worksheets represent. Okay. Please jump in and ask questions. Lab is intended to be a visual, interactive activity with the equipment out. And of course, you guys don't have the equipment out in front of you through no fault of your own, and you don't have quite as much visual cues as we'd like you to have. Okay, so now I'm going to say what I'd like you to draw on the worksheets. Maybe I'll just hold up a couple here. Here are some worksheets that people have done in past semesters. They've got a bunch of arrows drawn on the worksheets. And here's another one, which I'm going to show you better version of. See, just like a bunch of arrows have been drawn on this worksheet, and some of them are much larger than an 8.5 by 11 sheet of paper. Some of them are kind of double wide because the marbles flew so far that they landed, more than could be fit on a piece of paper away on the ground. So here I just held up a couple. 2 of the ones I held up are shown in the 2 of the ones I held up are shown on Lab 10 demos. So again, here's the worksheets. You're supposed to do the drawings on here. And here's what a final, oh, by the way, mass 2 for plastic, you could fill that in right there as 0.318. So mass 1 was steel. Steel collided with plastic, 0.318. In the previous collision, here's the first collision, steel on steel. So both masses are 1. It's really nice to multiply by mass 1 because you don't have to do a whole lot of work to multiply by mass 1. So most of the time, you don't have to really multiply by much, except for in the second collision, the plastic. So here is an example of somebody's handed in worksheet from a previous semester. So I'm just going to talk through this. I'm just going to give you a second, kind of just look that over. And isn't there another one? Trying to get to the second sheet. Okay, so there's another one there. So just take a second. I think maybe I'll stay on this one to describe first. This was a steel plastic collision. I see some things labeled with steel and some things labeled with plastic. Just look around at that for a little bit and see how the person labeled this. I would strongly recommend using some colors when you're doing this because it'll help visually distinguish information. So what did this start with? This started with just a mark here and a mark here and a mark here and a mark here. That everything grew out of those 4 dots. So what did the person draw first? The first thing they did is they just connected the origin, the collision site, to this location, and this location. And they labeled those V0 for velocity before the collision, V1 for after the collision, V2 for after the collision. The velocity vectors take very little time to draw. You just get out a straight edge and you connect the origin to these 3 impact locations. And let's see if they did about the same thing up above. This is going the other direction. This is kind of collision on the left, flying outward to the bottom right. But they just did light green to here and labeled it, or I guess they kind of did pencil, I think, color V1. And which one of these is V0? I guess that's the light green right there was that collision point. So this long one is V0, and this long one to here is V2. Looks pretty good. This is frustrating. Okay. And I'm going to go to here. Okay. This is the last page of the Lab 10 PDF, and it says vector analysis of conservation of momentum. First thing to draw are velocity vectors, and we've already seen that on our sheets. The next thing to draw are momentum vectors. On this person's, I'm going to look at this one because the colors are helpful for me. In this person's work, green was velocity vectors, and orange are momentum vectors. Now, how do you turn a velocity into a momentum? You multiply by mass. You scale the vector by the appropriate mass. What was the mass of the object that hit right there? Steel. So green gets multiplied by 1 to become orange. So V0 and P0 are the exact same vector on the worksheet. They've drawn them, the person who did this drew it twice in 2 colors, which I think is helpful, but they are the exact same direction and the exact same length. Why? Because this was a steel object. What about this impact point of the steel object after the collision? Well, V2 times 1 is P2, so V2 and P2 are the same. And then what about this one down here? This was plastic, and so here we see the scaling occurring. We see V1 is very long, but P1 is considerably shorter. How much shorter? Multiply by 0.318. So I think if you were to, print this one out and measure it, or if I were to measure it, because I actually have the actual guy right here, I think if I were to measure the green and I were to measure the orange, green times 0.318 would be orange. Okay, so that is step 8, vector analysis of conservation of momentum. Measure the length of each velocity vector and then multiply it by the mass of the associated object. This step is only really necessary for the marks left by plastic spheres. For any steel sphere, the momentum vector equals the velocity vector, since we are using units in which little ms is 1. So We've kind of talked through 7 and 8, and vector addition and comparison are coming up. Okay, remember what the collision was like. It was steel guy descended a ramp, steel guy descended a ramp and hit a stationary target. There was only one object moving before the collision, which was the steel guy. So there's nothing to add to P0 to get the total initial momentum, because the steel object before the collision was the only object moving. So not only is this P0, not only is this V0 and P0, this is like, I think what in the lab was called, capital P initial. Capital P initial is right there because it was the only object moving. Now, what do I have to do with this P2 and this P1? They both represent objects moving post-collision, after the collision. What am I supposed to do with P1 and P2? I'm supposed to do vector addition P1 plus P2 to get total final momentum, capital PF. How do you do vector addition by hand? How do you do vector addition graphically? So how did this person add P1 and P2? They left P2 in place and they picked up P1 and they shifted P1's tip to tail. So the tip of P2 becomes the tail of P1. Do you see that? P1 at the bottom is the same magnitude, same direction as P1 at the top. Now, in order to translate it properly, you need to measure the length of P1 and mimic it, but you also have to make sure you get the angle correct, and that's probably why the person labeled some angles here. I think the most important vector calculation or step for you to do is just to think through, how am I going to do P1, how am I going to move P1 properly to the tip of P2 so I can add them together. What I would do is, anyways, that's what I would say. I would probably do a little dotted line extending P2, just go dot, 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 dot up here, and then measure this angle orange to orange. It looks like in this person's work, it was 32 plus 15.5. So I would add those. What's the total angle there? 47.5 degrees. And whatever that angle is, I would mimic that angle up here from the extended dotted line to my direction of that I want to draw P1. I really wish I could show you guys this with rulers and things. It's really not too complicated, but you're going to need a protractor or something so you make sure that this vector is parallel to this vector. Do they look parallel visually on the screen? P1, P1, I hope so. So P2 plus P1 lands right there. So this purple vector from collision site to there is the final momentum, but this other slightly different vector from collision site to right there, and now I'm going to zoom in. So this is the final momentum vector. This is the initial momentum vector. Are they exactly the same vector? Not quite. The difference between them is a vector delta P that points from initial to final. So the core results of this work is P initial, bang, P final, bang. If the lab works out very well, those points are close together. The closer together this is to this point, the better momentum was conserved for this person's trial, for the trial shown on this sheet. Now, are they exactly the same? No. So the difference between them is a short vector. I want to emphasize one thing at least one or two times. Delta P is not the length of orange minus the length of purple. Delta P is however long this difference vector is from the arrowhead of orange to the arrowhead of purple. We've talked about this before. When you're adding vectors, you don't just add the lengths. It depends on the directions. When you're subtracting vectors, you don't just subtract the lengths. It depends on directions. So this is one example. Let's see. This is one example, steel, plastic, and this was very close to momentum conservation because those vectors are so close together right there. The other example is steel, steel, and it did not have, it had pretty good results, but not as good. I'm going to allow you to look at this. but here is P1, here is P2, which was translated from up above. They took P1 up above and they slid it to right here. So the bluish turquoise guy is final momentum. The light green vector is initial momentum. And in this case, they mismatched by a vector that looks to be about an inch long. So this was a little bit more change in momentum. And of course, we're expecting the momentum to not change. So that's a little bit more, that's a little bit further from the hope of the lab. The hope of the lab is conservation momentum. This was pretty good with a difference of about an inch. The previous diagram was really good with a difference of like a very short displacement, or a very short difference vector, P final minus P initial. But in both cases, somebody drew a vector that points from initial to final, and they labeled it delta P vector. Okay. Okay. What do you guys think? do you think that you could kind of trace that out for yourself? I would imagine that if you had the worksheets printed out, all the work for today's lab would last probably less than 30 minutes, probably around 30 minutes. Just straight edge drawing vectors. Almost every vector you draw comes from the collision site and sprays outward, except when you have to translate vectors in order to do tip to tail addition. So that is a basic overview of the activities to do on the two worksheets. Is there anything else to turn in besides the two worksheets? There is also an Excel file, which is called the data sheets, where you're just going to kind of take measurements with a ruler off of the worksheets and record the lengths of all key vectors. Record the lengths of all key vectors on the data sheet. Hiccuping. So what does the data sheet look like? So you'd want to measure this. You can see somebody wrote 11.05 centimeters, and they wrote 18.95 centimeters, 28.90, and 26.45. They should probably also measure this length. I would also measure this length in centimeters. And then the only angle you're asked to record is what is the angular difference between the turquoise and the light green. That's called difference in angle, or delta theta. So lengths of all the key vectors and the difference in angle between initial total momentum and final total momentum. And let's see what there looks like on here. Collision number 1, steel 1 on steel 2. Steel 1 goes down the ramp and hits steel 2. The next page says steel on plastic. What is the mass of a steel object? 1. So I filled it in. If it's mass, if it's steel, it's a 1. If it's plastic, it's 0.318. How fast is the second object going before the collision? Before the collision, it's not moving, so I filled in zeros. So you just want to fill in how long is that vector, how long is that vector, and then this plus 0 and get the total momentum. What about kinetic energy? Well, you guys know how to do kinetic energy. Kinetic energy is 1/2 times mass times velocity squared. So if you have the mass and you have a length for velocity, you can do that calculation and fill that in here, and then add 0 to get the total initial kinetic energy. And then same steps with final values. Not too bad. One thing I maybe should have done is, let me change this just a little bit. You see that one in blue there? To get the momentum total, I do not want you to add the magnitude of 1 to the magnitude of 2. I want you to go to your diagram and actually measure the length of your vector sum. So, oops, I messed that up. Excuse me, backing up, wrong red icon. So in this case, what was P1? What was P1? It looks to me like it says 11.05. What was P2? 18.95. Now, what do you get if you just add those together? You would get, I think, 30. 11.05 plus 18.95, I think adds up to be exactly 30. But did they write 30 right here? No, they actually did tip to tail addition and measured the length. They didn't say when you add vectors, you add the lengths. They added the vectors as arrows and they just measured the length. So do not add these two numbers to get this number. You can add kinetic energy 1 plus kinetic energy 2 to get kinetic energy total. Why can you do that? Kinetic energy is a scalar. Momentum's not a scalar, it's a vector. So maybe I'll kind of do this down below as well. So for that guy there, don't add these columns to get blue. You don't have to fill in total mass. You don't have to fill in total velocity. They're not very meaningful. You do need to fill in total momentum, but don't add these. You do need to fill in total kinetic energy, and you can just add because kinetic energy is a scalar. Over here, it doesn't matter very much because you're adding 0, so it doesn't change it. And then a nice summary. Before the collision, this is total values. It probably should say total momentum and total KE. Whoop, total KE. So that probably should have said that. So these are just the totals. I don't care about the 1s and the 2s in the summary table. I'm going for the totals. Okay. Oh, I went too high. Okay, so I want you to just take total momentum, put it in the summary, total kinetic energy, put it in the summary. What's the difference? And calculate a percentage difference. How do you get percentage difference? Difference divided by the initial value. P2 minus P1 divided by P1, or P final minus P initial, I should say, divided by P initial. Now, there's no angle to record for kinetic energy because it's not a vector, but there is a change in angle that I'd like you to fill in here for the momentum. And what would that be on the sheet? That would be this small angle right here, which for this person's diagram looks to be maybe just 3 or 4 degrees, a very small angle, difference in angle between light green and bluish. On this one, where's the angle? Oh, it's a teeny angle between orange and purple. So the two I showed you have pretty good conservation of momentum with small angular differences, just small angular differences. But there's an angle to record. And if you were to fill in all the blanks on the Excel sheet, which won't take you very long, and you were to draw in the vectors on the worksheets, which takes most of the time, you would have everything you need to submit your lab for today, sometime next week. All right. There's not a lot of calculations in today's lab. There's a lot of vector drawing in today's lab. Oh, shoot. Last thing I'm going to say, I knew there was something else. Screen share one more time. Promise this is the last one. Okay, what about units? What about units? There's no units for velocity, momentum, or kinetic energy. You can fill in velocity, just whatever you measure on the screen, on the worksheet in centimeters. Basically, you label these, measure these on the screen on your worksheet in centimeters, but just enter them there without a unit. But it's almost like we're using centimeters as a generic unit for any vector measurement. For velocity measurements and for momentum measurements, we're kind of using centimeters on the sheet as a de facto unit. Of course, momentum is not really measured in centimeters, but when you're drawing vectors, all that really matters about the vectors is the relative lengths of the vectors. And we can kind of use any unit of length to keep track of the lengths of the magnitudes of vectors. So there's a comment there. Kinetic energy, again, you don't really have to label any units. How do you calculate kinetic energy? 1/2 times 1 times velocity squared, and just enter the number here. Okay. How are people feeling about those things? 8.39 grams. Mass of plastic is 2.67 grams, and you can divide those by one another to get the scale values. As 0.318. Okay, so numbers over there in the chat bar if you're seeing the chat bar. Questions about that? If you feel good, you're free to go. It took longer than I thought, 55 minutes, but you're free to go. Tomorrow's class, I'll have up solutions to quite a few practice test questions, and we'll be kind of reviewing momentum and energy. Momentum and energy. I think it's somewhat helpful that today's lab is about momentum, because all we've really focused on since spring break is energy, but the test is about the two key conserved quantities in physics. The two most important conserved quantities in physics are momentum and energy, and that is the focus of Monday's test. If you're feeling good, you're free to go. If you got questions, please unmute and ask when other people are around to hear them. And if anybody missed this one or missed part of it, I'll be doing it again in about an hour. Thanks, Daniel. Stephen. Excuse me. Okay. You guys don't have to sign out. I'm just going to ask, do you have any questions? Because I'm going to be away from the Zoom view for a little bit as I look at emails that have come in the last hour. And they're mainly emails that have come in from you guys. Almost entirely